All right, so before we get started here, we're going to introduce next week's topic here today in this lecture. Your homework for this weekend, though, is going to be to look through your grade book and make sure that you don't have any disputes in terms of assignments being imported incorrectly or counted late when they shouldn't be counted late. All right. There are also instances of people completing an assignment on time but not actually submitting it, so then it gets counted late. For whatever reason, if you have any of these disputes, we're going to get them worked out now. That's your assignment for this weekend, is to go through your grade book, make sure that everything matches the way that you would expect it to be. If you don't have anything to dispute, you're just going to write none in your answer box here. And if you do have something to dispute, you're going to let me know the assignment and what the issue is. All right, but that's your homework for the week, is to make sure and look through the grade book. The Myopen math system's pretty good, but it's definitely not perfect. There have definitely been a few instances of it just acting crazy for no good reason, all right? The good news is that it logs everything that you do with a timestamp, so I can see exactly when it is that you attempted an assignment or a question, so that you don't get marks late if you shouldn't, okay? All right, so we're going to get started on this week. Our focus for actually today and then next week are going to be revolving around chemical structures. And then once we get the basis of that down, we can talk about the shapes of molecules. All right, and before we can get started here, we're going to have to review something that we talked about before, this concept of what are called valence electrons. Okay? And actually, we can go ahead and even say before that, something fundamental here is what's called bonds in chemistry. All right, a bond is the force connecting two atoms. I guess two atoms or ions. In a compound. Okay, so we've talked a lot about compounds. They consist of more than one element, more than one atom, and there's something that's connecting all those atoms together, and that force holding that compound together, we call those bonds. All right? Valence electrons are a type of electron in an atom, and they're really important because these are the electrons that are participating in chemical bonding. All right, valence electrons are also sometimes called the outermost or highest energy electrons. All right, they are physically the electrons that are held furthest away from the nucleus in the atom, and they're the highest energy ones. And again, the real important part about these valence electrons in an atom is that they're the ones that are going to participate in bonding. Okay? So an important skill that we need for this chapter is to look at the periodic table here and to be able to determine the number of valence electrons in a given atom. All right? And so it turns out that much like the charge that ions form, this has to do with patterns about where elements live on the periodic table, specifically what column they live in on the periodic table. All right? So again, we're talking here about number of valence electrons. All right, so it's actually pretty straightforward. Everybody in the first column has just one valence electron. Everybody in the second column has two valence electrons. All right, we're going to conveniently skip over this middle block here. What do we call that middle block of elements? Transition metals. We're going to conveniently kind of skip over the transition metals, and we'll revisit this topic after we lay down a little bit more complicated of a framework here. But for our purposes and for this next week, we're just going to kind of ignore those elements. All right? So then we're going to skip. Our next column has 3 valence electrons. Then you guessed it, 4, 5, 6, 7, and then our noble gases have 8. Okay? There is one important exception to this rule, and that is helium. Helium we put over there in that column, that noble gas column, because it behaves like a noble gas. It doesn't form bonds with any other atoms. It's a gas. However, helium is teeny tiny. It's only got 2 protons. So helium, the exception is that helium only has 2 valence electrons. All right, and again, you can kind of convince yourself of that. Its atomic number is 2. It can't possibly have 8 valence electrons. All right, every other element conveniently follows this pattern of, based on the column that it lives in, you can tell how many valence electrons are associated with that particular element. So if we said, for example, phosphorus, this lives in this 5th column here, that means that a phosphorus atom has 5 valence electrons. It has a total number of 15 electrons, because that's its atomic number. So if I'm holding a neutral phosphorus atom, it has a total of 15 electrons, but 5 of those electrons are what are considered the valence electrons. And again, those are the ones that we're really going to be focused on, because they are the ones that participate in the bonding of a phosphorus atom. The other 10 electrons are there, but they're not actually doing anything in a chemical compound. They're just kind of chilling around that nucleus, helping shield it and keep it all balanced. Okay, so this concept is going to be really important, all right? And when again, we're talking about molecular structures here. So the first place we're going to start is with what's by far the easiest of our types of compounds to understand in terms of structure, and those are our ionic compounds. Remember, ionic compounds necessarily consist of a metal and a nonmetal, all right? So for example, we're going to look at a compound that's formed between magnesium and sulfur. All right, magnesium and sulfur, both solids in their standard state, right? We can convince ourselves because they're black up there on our periodic table. Okay? These will come together to form the ionic compound magnesium sulfide, which is also a solid. All right, and how did I get that chemical formula? Well, remember, for ionic compounds, it's all about the charges. So magnesium forms an ion with a +2 charge, and sulfur forms an ion with a -2 charge. And those come together to make this compound magnesium sulfide. All right, so if we notice here, we're starting out with this neutral magnesium atom, and then it's becoming a magnesium ion. Likewise, we're starting out with this neutral sulfur atom, and it's becoming this sulfide ion here. Okay, so what we're going to do is we're going to picture this magnesium atom and this sulfur atom with their valence electrons. All right, and we're going to represent those valence electrons by dots. So my magnesium atom here should have how many valence electrons? 2. So we're going to put 2 dots on our magnesium atom here to represent the 2 valence electrons. And then we're going to combine that with our sulfur atom here. And our sulfur atom, if I have a neutral sulfur atom in my hand, how many valence electrons does that have? 6. So we're going to go around and put 6 dots. We're going to have to double up on 2 sides here. All right, which sides your dots are on doesn't really matter. Okay, so now, if these combine together to make that magnesium sulfide compound, my magnesium has to become a magnesium ion with a +2 charge. So when magnesium, the neutral magnesium atom, becomes the magnesium ion with a +2 charge, what is it going to have to do? Gain electrons or lose electrons? It's going to have to lose electrons, right? Because electrons are negatively charged. And in fact, it's going to have to lose 2 electrons. So which 2 electrons is it losing? Those 2 valence electrons. Likewise, my sulfide ion with its -2 charge. In order for sulfur to become the sulfide ion, is it going to gain electrons or lose electrons? Since sulfide has a -2 charge, it's going to have to gain 2 electrons. And so if we picture that sulfide ion with all now 8 of those valence electrons, all right, we can see now it's got 8 dots around there. Okay? And so this is just an example of an ionic compound, but this is a typical behavior of all ionic compounds. Our metals, they lose their electrons. And how many electrons do they lose? They lose their valence electrons, right? So the reason why this first column here always forms an ion with a +1 charge is because they got 1 valence electron. And when they lose that valence electron, they're left with a +1 charge. Likewise, every element in this second column forms ions with a +2 charge. Why? Because they lose those 2 valence electrons. Okay? A little bit more complicated, but on the same vein here, we have these same patterns with our nonmetals as well. Sulfur forms ions with a -2 charge, just like everybody else in this column here. That's because they gain 2 electrons. Okay? These ions are after what's called a complete octet. Let me get rid of some of these markings because it's getting a little busy here. Okay? And that is atoms are most stable when they have these fully filled shells with a total of 8 electrons. That's why we call it an octet. All right, so we can say our nonmetals accept electrons to a total of 8. All right, so if we look, for example, at fluorine, fluorine's got how many valence electrons based on the column that it lives in? 7. 1, 2, 3, 4, 5, 6, 7 valence electrons. So how many does it need to accept to get to that total of 8? Just 1, and that's why the fluoride ion, as well as all the other halogens, form ions with a -1 charge. Okay? This pattern also explains why our noble gases do not form ions. They already have complete octets. They're already happy with the number of electrons that they have. They don't need to be getting electrons from you or losing electrons. They're already perfectly happy and have their complete octet. Okay? So these nonmetals are going to accept electrons until they get a complete octet. All right, so let's summarize here. For ionic compounds, okay, our metals, they lose their valence electrons. They form those positively charged cations. Our nonmetals, they gain electrons, gain valence electrons to a complete octet. And that's why they form those negatively charged anions. Okay, so if we take an ionic compound like NaCl, that's a sodium ion and a chloride ion. Right, my metal has lost its valence electron, forming a positive charge. My non-metal has gained an electron, forming that negative charge. All right, so if we looked at a an ionic compound here, I'm going to represent my sodium ions in orange and my chloride ions in green. One of these ions has a positive charge. The other one has a negative charge. Right? So that ionic bond holding that compound together, right? Remember, bonds are these forces that are holding these ions together. So what's the nature of this force holding these ions together? What we would call an if we're trying to be all fancy and sciencey, an electrostatic force. Or more simply, opposites attract, right? Positive charges attract negative charges. So what's holding this compound together is simply that opposites attract force, what we call an electrostatic force. All right, so an ionic bond is again what we call an electrostatic force, which is a fancy way of saying the attraction between opposite charges. All right, positive charges are attracted to negative charges, so positive ions are attracted to negative ions. That's what's holding an ionic compound together. Okay? Importantly, what makes ionic compounds a little bit more simple than covalent compounds, which we'll discuss here afterwards, is that ionic compounds are always solids at room temperature. And in fact, in order to melt an ionic compound, you have to get ridiculously high temperatures. All right, molten lava would be an example, the only real practical example of a liquid ionic compound. And I think we all know that lava is not cold, right? That is a very high temperature substance. It's also created under extreme pressures. The bottom line is, in your everyday interaction, your interaction with ionic compounds will always be as solids. All right, and because of that, their structure is very simple. They're always just repeating arrays of positive and negative charge. Or, in other words, of cations and anions. All right, so we can picture this sodium chloride bond with one sodium atom and one chloride atom, but you're never just going to stumble upon one pair of ions out there in nature. They're always in these huge repeating arrays, right? So it's not just one, it's a bunch of them, all lined up next to each other, such that all the positive charges are interacting with negative charges, and vice versa. And this array will repeat in all directions, right? So not only do we have it repeating in this direction here, okay, but it will also repeat in 3 dimensions, right? So it's not just a plane, but if I wanted to be good, I'd have to put another layer, and then another layer on top of that. And it's going to get real ugly real fast, so I think you kind of get the idea here. All right, but the point being is that you have this infinite array of repeating positive and negative charges. That's what an ionic compound is, right? Positive, negative, positive, negative, positive, negative, all lined up next to one another. And for all intents and purposes, it just continues out into infinity, right? These things just grow and grow and grow in all directions. Okay, so structure-wise, they're very simple. They're just repeating arrays of positive and negative charge. And again, they're held together by that opposites attract interaction, right? The positive charges are all surrounded by negative charges. The negative charges all surrounded by positive charges, right? So we have that opposites attract interaction holding this solid together. Okay? All right, so, and the main focus is going to be now on covalent compounds because they are much more complicated. All right, so first of all, covalent compounds, they're a little bit more interesting because they can be solids, liquids, or gas at room temperature. So unlike ionic compounds, which are just always solids, covalent compounds can be any state of matter. You don't know just by the fact that it's a covalent compound what it is. Okay? As we've talked about, we call covalent compounds molecules. All right? These are the individual units of covalently bound atoms. All right, and a covalent bond is much more complicated than an ionic bond. In fact, the exact nature of the forces in a covalent bond is something that's a ridiculously complicated math problem that you would do in like quantum mechanics, all right? So we're going to kind of simplify things, and how we're going to think about covalent bonds. There's this one key word I want you to have in your mind when you think about covalent bonds, and that is the sharing of electrons. All right, these two atoms, they are bound together because they're both sharing this pair of electrons. Okay, another way to think about it is that these atoms are in a tug of war over these electrons. Okay, so if two atoms are covalently bound to one another, there's this pair of electrons in the middle, and they're both kind of got this tug of war going on, where they're both holding on to that pair of electrons. So you think about it as sharing. Sharing kind of sounds all nice and neat. Really, they're both trying to pull that pair of electrons. Neither of them are willing to let go. Okay? So these structures are going to be a lot more complicated. They're not just simply repeating arrays of positive and negative charge. Our covalent compounds are molecules. We have these clusters of atoms that are covalently bound to one another. And that's going to be the big focus of this lecture period, is just understanding these structures, and then next lecture period we'll be drawing them ourselves. All right? So for right now, I'm going to show you a picture of a covalent molecule, what we would call the Lewis structure of a covalent molecule. And how I got that, you're just going to trust me. All right? You're just going to trust me that this structure is correct. We're going to kind of pick it apart and make sure that we understand it, and then we'll worry about building them ourselves next class period. All right? So there are a few different representations of structures in chemistry, especially when you get to like organic chemistry, you kind of graduate to more complicated ones. Our beginner structures here are what are called Lewis structures of molecules. Okay, you will also sometimes hear these referred to as electron dot structures. They're pretty synonymous. I call them Lewis structures. Okay, so if we have a chemical formula, for example, H2O, We talked about how to identify that this was a covalent compound, because this is a compound of all nonmetals. All right, but we don't really know what this structure looks like. Okay, the Lewis structure of water looks something like this. All right, and we're going to pick apart exactly what this structure means. All right, this is going to be our example structure here. Okay, this is a Lewis structure. You have your oxygen in the middle and two lines, one connecting each hydrogen. Okay, and then there are these dots on that oxygen atom as well. Okay, this is what's called a Lewis structure here. And again, you have no idea how I got this. We're going to pick this apart and make sure that we understand what's going on here. All right, so, and then we're going to work, once we figure that out, then we'll work on taking this formula and converting it into this structure. But we're not quite there yet. All right, so understanding this structure. First of all, the lines in this structure, these represent the covalent bonds. Okay, so in a water molecule, it turns out that that oxygen atom is sitting in the middle, and it's covalently bound to one hydrogen on one side and the other hydrogen on the other side. All right, that's the structure of a water molecule. Each covalent bond, each one of these lines, represents a pair, two shared electrons. Okay, so each line in our Lewis structure represents two electrons, a pair of electrons that are being shared. All right, and again, we talked about covalent bonds, this sharing of electrons. So again, that's what that line represents. The dots also represent electrons. All right, you'll always see these dots in pairs. These are what are called lone pairs. Okay, these are, since they're always in pairs, they're two what are called non-bonding electrons. So these are electrons that are sitting on that oxygen atom, but they're just kind of chilling there all by themselves. They're not actually participating in chemical bonding with those hydrogen atoms. They're just a pair of electrons sitting on the oxygen. Okay? All right, so importantly, we need to look at this structure here. We need to be able to look at a Lewis structure and be able to count the total number of electrons. All right, each one of those lines represents a pair of electrons. Each pair of dots represents a pair of electrons. We need to be able to look at these structures here and see how many electrons are being represented in those structures. All right, so everybody take a second and total up. How many total electrons do you see on the board in this water molecule? All right, so if each one of these bonds represents 2 electrons, that means I have 4 covalent bond electrons. And then I have 2 lone pairs, so that's 6, 8. So I have a total of 8 electrons in this molecule. All right, when you're drawing a Lewis structure, making sure you have the correct number of electrons is like step 1, all right, to getting that answer correctly. So we need to be able to look at these structures and determine how many electrons we see. Okay, so now let's go to our formula here, H2O, and now let's total up the number of valence electrons in our molecule, right? Just given the formula, not looking at this structure at all. just given the formula H2O, we should be able to total up the number of valence electrons that are in that molecule. All right, if we go back to our periodic table here, let me get rid of these markings. We have this formula H2O. Everybody take a second and see if you can't tell me the total number of valence electrons that are in that molecule. How many valence electrons are in each of these hydrogen atoms? Hydrogen, the first column. 1. And if I have 2 of them, that means that each one's bringing 1. Now I'm going to add the number of valence electrons in an oxygen atom. How many valence electrons does oxygen have? Yeah, 2, 3, 4, 5, 6. So if we total up the number of valence electrons in this water molecule, we get 8. All right? Now, you had no idea how I got this valence structure of water, right? You just sort of trusted me that this was the correct valence structure. But the name of the game here is going to be to look at our chemical formula to total up the number of valence electrons. We said we had 8. That better match how many electrons are in your structure. Okay, and again, we'll worry about drawing these structures here in a bit. We're just trying to make sure that we understand what we're looking at when we look at one of these Lewis structures. How many electrons do we see down on the board? How many bonds do we see? How many lone pairs do we see? All right, so I'm going to put down a few more Lewis structures here, and you're just going to trust me. All right, and for each one, you're going to tell me the number of covalent bonds, the number of lone pairs, and lastly, the total number of electrons. Okay, so if we're going to look at our molecule here, we have 1, 2, 3 covalent bonds. Okay, we colored those in orange. We have 1 lone pair, and thus gives us a total of how many electrons in this structure? Each bond represents 2, so that's 2, 4, 6, plus my lone pair. I have a total of 8 electrons in that molecule. Okay, looking at this molecule, oxygen difluoride, we have 1, 2 covalent bonds. And we got a ton of lone pairs going on here. 2 on the oxygen, and then 3 on each fluorine. So that's 6, 7, 8 total. Oops. All right, so then if we count up the total number of electrons in this molecule, how many do we have? 20. So 2, 4 for my covalent bonds. Then I got to count each pair of electrons. 6, 8, 10, 12, 14, 16, 18, 20. A total of 20 electrons in this molecule. Okay, and then this last molecule here, how many covalent bonds? 4, 1, 2, 3, 4. All right, how many lone pairs? Each of these chlorines have 6. 1, 2, 3, 4, 5, 6. I guess each had 3, for a total of 6. And then how many total electrons do I have in this molecule? 2, 4, 6, 8 from my covalent bonds. 10, 12, 14, 16, 18, a total of 20. Okay? And you want to convince yourself that just starting with that formula, CH2Cl2, if you totaled up the number of valence electrons in this molecule, you would also get 20. Okay? According to our periodic table, each carbon has 4 valence electrons. Each hydrogen has 1, and I have 2 of them. And each chlorine has 7, and I have 2 of them. So that gives me a total of 20 valence electrons from that chemical formula, right? So again, that's what's going to be the name of the game. Given the formula, you're going to total up the number of valence electrons. That's got to match what you drew in your structure. And again, we'll talk about how we draw these structures next week. We're just making sure we understand what we're seeing here. Okay? 2 more important points about these Lewis structures. One would be what we would call double and triple bonds. Okay, so for example, oxygen gas we know is diatomic. So is nitrogen gas. The structure of these 2 molecules looks like this. All right, so between, if we want to focus on this oxygen here, we see that these 2 oxygen atoms are connected by 2 lines. All right, this is what we would call a double bond. Each line, again, represents 2 electrons that are being shared. So a double bond means that there's a total of 4 electrons being shared in that covalent bond. All right, again, each line just represents 2, so 2, 4. We got a total of 4 shared electrons in that double bond. All right, my nitrogen molecule is held together by these 3 lines here. And we're really creative, so this is what we call a triple bond. How many electrons do we think are being shared in a triple bond? 6, right? Again, each line just represents 2 electrons being paired. So a triple bond means 6 electrons are shared between those 2 atoms. Okay. So the last thing that we want to do looking at our structures, this is going to be one of the checks that we use to make sure that the structure that we're looking at is actually correct. All right? And again, I've given you all these structures, so let's just verify that they meet what's called the octet rule. We talked about the octet for ionic compounds, how metals want to lose all of their valence electrons, and nonmetals are going to accept valence electrons until they have a complete octet. We have a similar octet rule in covalent compounds as well. All right, so atoms will share electrons, right, i.e. form covalent bonds. To complete their octet. All right, so for most elements, we have to put this caveat most on it, and I'll explain that here in a second. The octet rule means 8 electrons. So let's look at one of our structures that we had done before. That oxygen difluoride. The reason that oxygen is willing to form this covalent bond with fluorine and fluorine's willing to form this covalent bond with oxygen is that both of them are trying to complete their octet. All right, so that's why elements will engage in bonding to begin with, is they want that complete octet. So when we look at our Lewis structure here, one of the ways that we're going to know that this is correct is that each element is quote-unquote happy, meaning each element has a complete octet. All right, so if I look at my fluorine here, it's got these 2, 4, 6 electrons in lone pairs. But it's also got this covalent bond associated with it, which is worth how many electrons? 2. So indeed, my fluorine here has its 2, 4, 6, 8 electrons, its complete octet. So fluorine's happy, right? It was willing to form that covalent bond with oxygen to share that pair of electrons because that brought it up to that total of 8. All right, but all of our elements better be happy in our molecule. All right? So now let's look specifically at the oxygen in the middle. All right, we said that the fluorine has a complete octet. What about the oxygen in the middle? How many electrons are associated with that oxygen? Again, it's got 2, 4 electrons in a lone pair, but it's also got these 2 bonds, so that brings it up 6, 8. All right, 2, 4, 6, 8. It indeed has a complete octet. Okay, And we can convince ourselves that the fluorine on the other side is the same as that first fluorine. It's got three lone pairs and 1 bond, bringing it up to a total of 8. All right, so that's why elements will form bonds with other elements, is to complete their octet. Now there's important exceptions to this rule. We said most elements, their octet rule is 8. That's where that name comes from, the octet rule. All right? There are some elements, though, that are exceptions to this. We still call it the octet rule, but they require less electrons. The most common one is hydrogen. Hydrogen is so teeny tiny small that in order to complete its octet, it only needs 2 electrons. Okay? So if we go up to one of these molecules up here that contained these hydrogens. So nitrogen wants how many electrons in its octet? 8. It's not one of our exceptions, right? And so indeed, 2, 4, 6, 8 electrons about that nitrogen. But if we look at each hydrogen, right, focusing just on our hydrogen here, each hydrogen only has 1 bond. Each bond is again composed of how many electrons? 2. And those 2 are all hydrogen needs to fill its octet. It can't fit anymore. It's too teeny tiny small of an element. All right, so hydrogen, our octet rule is just 2 electrons. Okay, the other exceptions are these other 2 small elements here. I think it's easier to identify them on the periodic table. Helium also only needs 2. It has 2. That's why it doesn't form any bonds to begin with. All right. Importantly, beryllium and boron are also exceptions. Elements 4 and 5. All right. Just to complete our list here, beryllium only needs 4 electrons to fill its octet, and boron needs a total of 6 electrons to fill its octet. All right, so these are our octet rules that we're going to use when we're forming covalent compounds. For most elements on the periodic table, the octet rule is 8. That's where the name comes from. All right, but there are these 3 exceptions we have to note. By far the most important is hydrogen. This is the one you're going to see over and over again. That only needs 2 electrons to fill its octet. Beryllium and boron are also exceptions to our octet rule. All right, we'll focus on drawing these structures next class.